Hello, everyone. Thank you again for the introduction. I would like to talk about my experiences with the OpenAMP framework for asymmetric multiprocessing. I've been working at Forth for almost 1.5 years now. So, the mission statement is effectively task offload in a heterogeneous ISA system. Riser's goal, more specifically, is to achieve this task with an ARM host to be applicable to existing infrastructure, benefit from ARM reach, the rare chips, and so on, that is running Linux. The host will then be connected to accelerators, or co-processors, often referred to, via PCIe, as well as QSFP connections from accelerator to accelerator. And the accelerators are currently being developed through EPI and EU Pilot, as you very well might know, and will in the end utilize a real-time operating system, or RTOS. Currently, our efforts, and my efforts more specifically, are to attempt task offload on non-final hardware and approximate as closely as we can the final systems that will be deployed across Europe as closely as possible. This will involve understanding the practical workflow of such a concept in the real world, solving any issues and completing necessary background work in parallel with all the hardware efforts to try and get ahead. Between all the hardware efforts, similar work on the EPAC chip, which, as Manolis Marazakis showed earlier in the overview slide, is currently connected to an x86 host in our case, as well as the following test platform, the one I'm working on. We want to capture as complete a picture as we can of the behavior expected in the final systems. Firstly, a short overview of OpenAMP and libmetal. What is OpenAMP? It's a high-level framework that enables interprocessor communication, resource sharing through virtual I/O, vRings, and so on, and takes the remote proc concept that is prevalent in Linux for remote processor management and allows it to be used in conjunction with other heterogeneous systems. So takes it out of Linux space and makes the necessary abstractions for such a system to work across different systems. It is built on top of libmetal, which is a low-level abstraction layer for memory, devices, interrupts, and so on, effectively hardware, and works across heterogeneous systems as well. Its APIs are inherently OS agnostic, so they work on a multitude of OSs, and they can also be custom implemented for non-supported OSs, which is what enables OpenAMP to be portable and allow such abstractions as vRings across systems and environments. We can also see on the bottom right here, I think you can see my mouse cursor, we have Linux apps, for example, RTOS apps, running on different cores in a system with their own ownership on some memory, since that is required in many cases, and they have shared memory spaces, perhaps mailbox drivers that are utilized and so on. And they can also all share peripherals. So next up, we can take a closer look at the testbed, which in our case is the Milk5 DuoS development board. This board was chosen because of its unique hardware design, as much as we'd love to use a European board at the time, which is end of Q3 2024. There was no such device, so this is from Milk5, which is a Chinese company. So this board allows us to have a RISC-V big core and the RISC-V small core, the big one running Linux and the small one running FreeRTOS. Or in our case, which is more interesting and useful for Riser, we can also run it in a configuration of an ARM A53 core running alongside the RISC-V RTOS core. It's a C906 by Huanti. So that is why we've chosen this board. Also on the build system side of things, it's an open source build system, so we can intervene, we can customize it how we want, and bring it as much as we can closer to what Riser aims to be. So we can more closely approximate the final deployment, I should say. Next slide. So, what does the internal architecture look like? Internally, the system exposes a simple mailbox driver and registers that can be seen bottom left here. This is just taken from the devices tree. Yes?
Sorry, I thought you changed your slides. No.
No. So as we can see from the board's device tree, we have a mailbox driver that just exposes a few registers to both, effectively to Linux, but the registers are owned, quote unquote, by FreeRTOS. And we can then program custom functionality into FreeRTOS and commands and have Linux call these commands via the mailbox. Also, of course, FreeRTOS could also send back results and data through the mailbox back to Linux. Aside from a small area of ownership between the two kernels, the systems can both address the entire onboard memory. So aside from a very relatively small area of kernel ownership where it's protected, the memory, both processors do have access to the entire memory space, which for this board is 512 megabytes. And this means that we can very closely emulate the final system, as we have a Linux ARM core, like we'll have with the SiPearl chips, and we have a RISC-V secondary RTOS core. Also, the system, as we'll see later, is tightly integrated, so we don't need to worry about, quote unquote, any PCIe overhead or signaling or really communication layers in general. We can focus more on the software stack and the workflow. And then we have other efforts and other parallel works, let's say, with EPAC for the PCIe interconnects and stuff. So using this testbed, we're trying to emulate Riser, the final deliverable of Riser, as closely as possible. And we also want to test different ways that co-processing could be achieved in the final hardware. Again, workflow problems, mainly top-level concepts. So a quick overall look again. There's the board. You might be able to see in the picture as well, under the port here, there is the hardware switch to switch between RISC-V and RISC-V big little configuration and ARM and RISC-V big little configuration. We can see here a block diagram as well. There's ARM Linux. That's what we're focusing on, connected via the mailbox to the FreeRTOS system. And here we can see as well the block diagram for the chip, where we have the FreeRTOS RISC-V core. Again, it's a C906B, I believe, CPU core. And here we have either the RISC-V C906 for the big Linux core or the Cortex A53. And these are tightly integrated on chip, on package. And at the bottom here, we can see a short summary, effectively, of how OpenAMP can help us with this, where we can use RP-Message for transport layer communications, Virt.io for Mac, so they can share devices and such, and it's all built on top of libmetal. and host gets ownership of remote proc to boot and manage the coprocessor. Should also mention, during these efforts, we created a testing suite for libmetal, which it had some tests, but they were very outdated, and using custom in-library testing, we instead generalized it on the system and the OS level. So we have a cross-platform testing suite that is now part of libmetal. It's upstream. Next up, the progress so far. We can only run OpenAMP for intra-core communication using RP message, VRings, and shared memory on the Linux side, whether that be a RISC-V or an ARM big processor, as well as in QEMU, as libmetal is a prerequisite to initialize properly, and libmetal isn't yet completely implemented on FreeRTOS. We have managed to run libmetal in a slightly pared down version and make use of it between the two cores and the mailbox driver, but the libmetal FreeRTOS implementation, again, is still relatively incomplete. That is all so far. Regarding the operating system, we've also customized the Linux side of the testbed, mostly regarding inter-core communication, exposed devices, and the mailbox driver. That's needed some work from our side. We've also added some custom commands and tweaks to FreeRTOS that can be called from the Linux side to be executed by the FreeRTOS side, which is not only useful for development and furthering the testbed's capabilities, but could prove beneficial when evaluating co-processing as well. So we can effectively take custom commands, put them into the FreeRTOS kernel, into the OS, and then we can repeatedly call them from Linux as we see fit through the mailbox driver. Next steps are as follows. The libmetal library needs to be fully implemented for the small core, which can be done one of two ways. We can continue with FreeRTOS and implement the missing modules from scratch, which would perhaps be the quickest and safest option to quickly test and iterate on ideas and concepts. Or we could also switch to Zephyr OS, which is a real-time operating system run by the Linux Foundation. Zephyr does have built-in libmetal support and is significantly more versatile and fully featured as an operating system, but it would be quite a bit more work on the firmware side. In our case, we'd need to completely boot the secondary processor effectively from zero with Zephyr, reallocate memory spaces between the OSs, as Zephyr's requirements are markedly higher compared to FreeRTOS, as well as modify the mailbox driver once again to port it into Zephyr. Next up, OpenAMP also needs to run on the small core. Main roadblock there being the simple requirement for libmetal. OpenAMP is also supported by the Zephyr operating system out of the box, which is another positive should we choose to go that route in the end. Last but definitely not least, we need to evaluate the best course for coprocessing and what form that could take. For instance, like I said earlier, frequent operations, should we discover any in our testing, could be pre-programmed into the RTOS core, like we've already done with FreeRTOS, and then called on with certain parameters, perhaps, as opposed to repeating complete binaries and the overhead that would come with that. So, for example, in the case of matrix multiplication, instead of passing an entire binary of a matrix multiplication program and then having the small core accelerator run it, we could instead code a matrix multiplication command into Zephyr and then pass however many arrays we need to multiply. And then we just get the result back. Binaries would have to be generated via toolchains before execution. When and how do we do that? That's something that we need to evaluate. And on a significantly more out of scope note, this platform, the dev board with OpenAMP, should allow us to test the possibility of achieving arbitrary binary execution instead of cross-compiling via dynamic binary creation, just-in-time compilation, like we have with Java and Python. So then we don't even effectively need the source code. We just run the same thing on both sides, as well as direct binary translation in the case of simple binaries. In the end, we are attempting to figure out the entire workflow as proactively as our testbed allows to make the transition to the final hardware as smooth as possible.